Okay, so welcome to another lab. In this lab, as we covered, we're going to be designing a distributed Bragg reflector. Let's start from here again. Uh, so these reflectors are commonly used in many areas. One of them is basically nanolithography. For lithography, we basically try to transfer a pattern on our wafer, on our substrate wafer. We try to create a pattern on our wafer. For that purpose, we need first of all light, the light source. And people are trying to narrow down the sizes or shrink down the sizes of the transistors. So they're now searching for even smaller scale, wavelength scale light sources. For that reason, one of the things that they come up with is to use extreme UV light sources. Okay, but remember that these light sources, for example, in this case, they settled down for 13 nanometers. At these wavelengths, your projection systems, like the lenses, will be very lossy. The quartz lenses will be very lossy, so you have to do something else. This is our extreme UV mask. Whatever pattern we have on the UV mask will be hopefully reflected back and will be transferred to the wafer. For that purpose, we need to really very efficiently reflect the light back from the extreme UV mask. Okay, so here is the design that people came up with already. They are cascading several layers of molybdenum and silicon on top of each other. Okay, and the lab is basically asking you to find the smallest amount of layers that we can use. All right, so what do we do? To create our pattern, we first need a very absorptive material on certain areas, like aluminum, chromium, tungsten. These kind of materials are very lossy, so we pattern them here in these kind of designated coordinates, and thereby we have these openings in the middle. When the light comes from the top, it will be reflected back from these openings, whereas it will be absorbed in these sides. Okay, since the wavelength is very tiny, there won't be hopefully too much diffraction mechanism happening. Okay, while the light is getting out, for example. This is, after all, another grating. As we covered, it can really end up with diffraction patterns. All right, so and then they came up with this kind of a design that I shared with you by cascading molybdenum and silicon at 13.4 nanometer exposure wavelength. And the question is asking and already giving you like the dimensions as well. 2.76 from molybdenum, silicon is 4.14. One important thing to remember is the atomic number of these two elements. Molybdenum is a heavy element and silicon is a lighter element. And for element, the weight, you know, people generally use the label Z. So this is the high Z element, that's the low Z element in comparison to molybdenum. This is our exposure wavelength, where after TE waves at normal incidence. So this is very similar to what we have done so far, a one-dimensional photonic crystal, and we want to achieve over 70% reflection. So let's see, I'm gonna switch to that paper. Yeah. Okay, so this is the paper that I uploaded, and you are going to look up these kind of tables here. That's our exposure wavelength, and the N and K values for these different materials are given here. How are you going to use them? So let's go back to the code. Here's the code. Let's run it. Okay, the exposure wavelength is asked. Exposure wavelength is going to be 13.4 nanometers. The incidence angle, normal incidence 0. The number of alternating layers. So that's the thing that I want you to find out. So I'm going to just start with a more naive number, 25. Enter the high Z refractive index. That's asking me the higher atomic number elements refractive index. That's molybdenum, if you remember. And its refractive index is this much. Luckily, MATLABs give you the opportunity to recall these kind of numbers once you enter them previously. Looks it up from its history and enter the thickness for high Z elements. So that is 2.67 in nanometers, as I gave you. The other element is 4.14 nanometers. Okay, so this is the reflection spectrum that we end up with. I mean, we don't really need to measure it too much, but let's just, for the sake of doing it, I can see that we went up to slightly over 40% of reflection. So, okay, we've got some, and it's covering this band, but the highest point is basically at the exposure wavelength, still needs a lot of improvement. It's too low compared to our 70%, the aim goal. So I want you to enter different layer numbers and try to guess which direction I should go first. Should I go higher from 25 or should I go lower? And then the exact number. All right, so please see you in another lab. Bye.